Hello everyone. Today we will be solving the problem of Leetcode daily challenge, that is K inverse pairs. The problem statement is for a given integer array nums, an inverse pair is a pair of integers I comma j such that I is less than j and nums of I should be greater than nums of j. Basically, it's the standard problem of inversion counting, but here we will be given two integers n and k, and we need to return the number of different arrays consisting of integers only between 1 and n, and there can be exactly k inverse pairs. And finally, since the answer can be large, we need to output it modulo 10 to the power 9 and 7. So let's us check the second example. Here n is 3 and k is 1. So we need to use 1, 2, and 3 to make our arrays. So the only possible arrays with exactly k inversion count will be 1, 3, and 2, and 2, 1, 3. In 1, 3, 2, the inversion pair is 3, 2, and in 2, 1, 3, the inversion pair is 2, 1. Okay. So what would be the most brute force approach to solve this problem? We can generate all the permutations of 1 and n, 1 to n, and then check the count of inversion pair in a specific permutation. If that is equal to k, we increment our answer, and then finally we output the count of arrays, different arrays that we get. So what would be the time complexity for this approach? First of all, we need to generate all the permutations, which will itself be n factorial. And for each of these permutations, we need to check the count of inversion pairs, which will be n log n if we use either merge sort or Fenwick tree to count this. It's a standard problem to find inversion count. So for those who are not aware of this, I would recommend you all to suggest to go to maybe Geek for Geeks or Leetcode and try to solve this problem. So if I were to share my code for the brute force approach, so first of all, we have this boilerplate code which takes the integer n and then creates an identity permutation. So what is an identity permutation? It is basically a permutation containing all the integers from 1 to n in a sequential order. Then we use the standard C++ template function of next underscore permutation to generate all the permutations of a given vector. And then for each permutation, we first of all retrieve the count of inversions in that specific permutation. So in the int get inversion count, we get the nums, that is the current permutation, as a parameter. We then initialize a Fenwick tree of size n plus 1, and then we iterate from back. For each element in nums, we try to find out how many smaller elements have been encountered till now, which will be given by the prefix function of the Fenwick tree. And then we increment this smaller count to the inverse count variable. And finally, we return the inverse count. So we do that for every such permutation and check if that inversion count is equal to k. If it is, then we increment our answer and then finally we return it. This approach would definitely TLE because n factorial is quite a huge complexity, and also if we check the given constraints, n can be up to 1000 and k can also be up to 1000. So n factorial will definitely not work here. So what other approaches can we think of? One specific idea that we can think about is using recursion. Now, the main idea of recursion is we need to keep two parameters. First of all, I and j. What does I and j specifically denote? I denotes that we will consider all permutations having elements only between 1 up till I. That is, permutation of I, permutation of any index j can have the maximum upper limit of I and the lower limit will be 1. And j denotes how many permutations with having maximum element as I can have exactly j inversions. So the recursive function would look something like this. Let's say I get solve and I need to take, let's say, I and j. The main idea is, if we have already pre-computed, say we know the answer, that how many permutations having elements, if let's say if we know the, let's write it here, if we know the count of permutations having elements between 1 and I and exactly j inversions, we can do that. We can find the subsequent answers for I plus 1 elements as well. Now how? That's the main question, right? As soon as we introduce the I plus 1th element, it becomes the largest in the current set of elements that we have. So what all possible choices are there to place the I plus 1th element? We can either place it at the end of the array, that is our initial permutation, and the I plus 1th element. Or what we can do is place the I plus 1th element just at the second last index. This was this, and this was the last value. Or maybe place in the third last index, second last value, and last value. Similarly, till the beginning of the array. So if we place the I plus 1th in value element at the end of the array, we won't get any extra contribution due to this. Because if we have a look at a permutation, 1, 2, let's say 5, then 4, and 3, then 6. Here n equal to 6, and the last element, that is 6, is placed at the end of the array. So you won't, if you observe carefully, you won't find any I comma j such that j is 6 and I is something else, and the value at index I is greater than the value of index j. That's trivial because the last index is the greatest element and it will not contribute to any inversions. So our answer will be same as the previous solve that we got for I and j. If we place at the second last index, that is the I plus 1th value, so we will get one extra inversion due to this. Because let's say in our initial permutation, instead of this conversation, we had the 6 and 3. So due to 6 and 3 constitutes one single pair, which will give us a new inversion count. So this will be same as having I minus 1 elements and j minus 1 inversions plus 1 added due to this new I plus 1th element. Similarly, it will be for I minus 1, j minus 2, and added 2. If we observe carefully, there is a recurrence relation that is being uh, uh, observed here. Say solve of I comma j is same as, let's say, solve of I plus, or let's say I. Solve of I comma j is same as solve of I minus 1 j plus solve of I minus 1 j minus 1 plus solve of I minus 1 j minus 2 up till minimum of j minus minimum of I minus 1 comma j. This is the recurrence relation involved. So why do we take this minimum of I minus 1 and j? Because if we exceed it, it might happen that we get a negative index here. That won't give a valid answer. So we always consider those values to be 0 and don't consider them in our answers. So this is the recurrence relation involved. So if we try to write a, maybe using memoization, then it's a simple DP. What could be the states? DP of I, which denotes elements from 1 to I, and j denotes exactly j inversions. will be equal to dp of I minus 1 j plus dp of I minus 1 j minus 1 plus up till so on dp of I minus 1 and j minus I minus 1 if I minus 1 is greater than or equal to less than or equal to j. So this will be our recurrence relation. So we can iterate for every j, and that is the index that we place the last element, and we can subsequently find our dp transitions. So if I show you my code, so we create a dp table of having the parameters n plus 1 and k plus 1. Initially, the base case will be if we have 0 elements, and obviously then we will have 0 inversions, right? So dp of 0 comma 0 will be 1. Now we iterate for every I, having I being elements from 1 to I, and every j from 0 up till I minus 1. What exactly this j denotes? This j denotes at which index, after which steps am I placing the last element that I'm currently adding here. Then we have a parameter of capital K, which denotes the current number of inversions that we need. So if k minus j is greater than or equal to 0, we have dp of I comma k added by dp of I minus 1 k minus j. This is same as the one that we showed here. If we see this, this is same as the recurrence relation that we had here. We iterate for every j minus 1, then minus 2, and so on. And then we decrement the state value of the current number of inversions. This is being done here. And finally, we return dp of n comma k. So let's analyze the time complexity for this. The time complexity will be big O of n into k. That is n square k. And the space complexity will be, we are using n into k dp table. So big O of n into k. Now, if we closely observe, this time complexity is roughly equal to 1e9, since n and k both range up till 1000. So we cannot use a n cube dp solution here. So we need to find some observations. What observation can we try figuring out here? The first observation will be, are we doing any redundant step? So first of all, we need to clear out few things. There are some absolutely necessary conditions in this problem. What are those? The two state values of the dp table that we are having currently. Those cannot be neglected. We need to have those state values of the current prefix of values that I'm taking and the current number of current number of inversions. So we can only do is optimize in the in the manner in which we are doing the transitions. If we clearly observe this simple mathematical formula, let's say dp of I and j, the one that we wrote there, is equal to dp of I minus 1 j plus dp of I minus 1 j minus 1 plus up till dp of I minus 1 j minus I minus 1. Okay. What will be the value of dp of I minus 1 and j? It will be dp of I minus 1, let's say maybe dp of I and j minus 1. It will be dp of I. We are following the exact same transitions that we wrote here, and try replacing j by j minus 1. It will be, and I by I minus 1. It will be I minus 1 j minus 1 plus dp of I minus 1 j minus 2 up till dp of I minus 1 j minus and this will be j minus I, right? So what if we subtract equation 1? Let's name this as equation 1 and let's name this as equation 2. What if we do 1 minus 2? Why are we doing subtraction? Because the first thing we need to observe here is what are we trying to achieve? Let's get that clear first. We want to remove these transitions and try to deduct some mathematical formula so that we don't have to do these summations, because this was summation that took an extra big of n complexity. So our main goal is to remove that. And why are we exactly subtracting? Because we see that some of the values are repeating here. If we clearly observe, dp I minus 1 j minus 1 is appearing in equation 1 as well as in equation 2. So dp of I j minus dp of I j minus 1 will be equal to dp of I minus 1 and j, that is the first value, as plus minus dp of I minus 1 j minus I. And we can finally, so finally we get this equation, and dp of I and j will be dp of I j minus 1 plus dp of I minus 1 j minus dp of I minus 1 j minus I. So we can clearly see we can derive the current value for particular state using the values of our previous state. So this computing this would take just big of one time complexity, because all we are using is the values of the previous row. So if we see the code for this, it will be pretty this I guess sufficient. Yeah. So let's code this up, right? Yeah, fine. So first of all, we need to output our answer modulo 189 plus 7. So also let's create a helper function of adding two integers and returning them modulo the prime which are given. So this is the one, and let's create the DP table that we were referencing in our explanation. So DP of n plus 1, k plus 1, 0. As we said, having 0 elements equal and 0 inversions, the value would be 1, and then comes our transitions. For each k value, uh, j equal to 1, j less than equal to k, I denotes the values up till value I, that is from 1 till I, and j denotes the current number of exactly that many number of inversions that we are having. So that let's use the comment state transitions that we had used. These were the ones. So we can see here dpij will be addition of dpi and j minus 1 and dpi minus 1 and j, and if j minus I is greater than equal to 0, because we don't want to give a negative index to a array size, that being dpi comma j equal to subtraction of dpi and j itself and dpi minus 1 j minus I. And finally, we need to return dp and comma k. We haven't created a helper function for subtraction. Let's do that. Int sub int b return a mod minus b mod, but leaving it this would give an error because it might happen that the b modulo mod value becomes greater than the a modulo mod, and we know that it cannot be negative, so we also do a plus mod here so that our resultant doesn't become negative. So let's run this. It's getting wrong answer. Let's try to figure it out. What's wrong in here? Okay. Okay, I see what mistake we did here. Because having 0 inversions, there is always a base case. So we missed a base case here. This base case is necessary because let's say, what does I exactly denote? I denotes we are having values from 1 up till value I. So there is always a permutation that is ident permutation, that is 1, 2, 3, and 4. In this case, the number of inversions will be 0. So having values up till index I and 0 inversions, the values will be 1. Let's try this now. Okay, it's running. Let's try submitting it. Yeah, it passed. So it was a pretty nice problem. The main trick was involved in this optimization. The transitions had to be optimized to reduce the time complexity from big O of n cube to n square. There is also one more optimization that can be done here in space. We are currently using n square space, so we can also do it in big O of n space. Why? Because we are only referencing for each specific state I comma j, we are only using values of the previous column or previous row. So we don't need the n plus 1 here. We can just do it using 2 steps. And we just use the parity of it, of the row. So this parity trick saves us from using the entire n plus 1 rows. We can just use 2 rows to use the current and the previous row values. And why does parity works? Because it alternates between 0 and 1. So if I start with 1, that means the current row. That means 0 was my previous row value. So let's try running this. It works. Let's try submitting it again. So we can clearly notice a very 10 MB difference in space because we reduce it from n squared to big O of n. That's all for this problem. Thank you, everyone. See you next time.